Okay, so I can go ahead now.
Yes, sure. Thank you.
Okay. So hi everyone, I'm very happy to be actually part of this school because unfortunately I didn't listen to all the lectures, but the ones that I heard are really amazing. So I hope, for your students that it's very useful experience. So what I will try to do. My title is Gamma Ray Dark Matter Searches. So I will try to go from basically use what people what people told us already, material that you heard already, sort of to put it in the context of dark matter indirect search. And then my talk should be sort of introductory talk to the talks of Francesca and Manuel that you will be hearing in the next days. So let's see if I manage to do this job well. Okay, so I will also follow the tradition of some of the lecturers to introduce myself. I thought it was very nice. So I work in Slovenia at University of Nova Gorica. And so since this is rather new and a small university, I think not many of you got a chance to be here. So we are sort of located in this valley in Slovenia, and hope to be able to host you at some point as well. All right. So so there is no need for introduction, but I just wanted to sort of establish, to just mention that, of course, we have huge, very large evidence that dark matter is a building block of the cosmological model. And just wanted you to not, to underline that we have many evidence for this fact, but it's all of gravitational nature. Okay, and it's all in remote astrophysical systems. So we study systems from large scale structure to dwarf galaxies, and in all of them we see this evidence, but not really necessarily on Earth. And so if one talks about astrophysical dark matter searches, there are two sort of categories that one typically takes into account. One are exactly this fact that so far we know it only gravitationally. So one thing is that we want to find non-gravitational evidence for dark matter. So we want to find the way it couples to standard model and to learn about new forces on dark sector in general. And this is what is typically called, at least in my opinion, indirect dark matter searches. While there is another category that one can also study, look for dark matter properties in astrophysical systems, but via gravity, because argument for this sort of approach is we know that dark matter interacts gravitationally. It might not interact actually with any other force. This is not a given. And so at least let's explore gravity to its maximum and study gravitational systems, small scales, to determine its properties, at least its mass, does it have self-interactions or so. And so I will focus on these indirect dark matter searches via gamma rays, of course, in this talk, but I believe that some of these second point you heard already in Jesus's talk, Jesus's lecture at the beginning of the school. And so I also decided to spend few sort of big picture words about the philosophy of this all, because sometimes, in meetings or, in the view of some people, one could wonder, why do indirect searches at all? In a sense, astrophysics is messy, and so necessarily there is many unknowns in those systems, and so searching for fiber signals of dark matter is necessarily challenging. And so this is a bit different, of course, than in direct and collider searches here on Earth, which are cleaner environment. There are also complicated backgrounds there, but they're at least controlled systems. At least we know more or less what goes in. Yes, of course, the argument is that we need to look for dark matter remotely in these systems where its gravitational evidence is clear to exist. And also indirect searches often provide a link to early universe physics. So sort of by discovering it in astrophysical places, we can learn also something about how it came to dominate the universe. And then, of course, multiple handle on its properties are necessary. Another thing is that astrophysical experiments, so we need to use astrophysical experiments for indirect searches. And of course, those are not prioritized for dark matter, again, as a difference from lab experiments. So they have different priorities, and basically are focused on discovering, astrophysics, but it is also a plus because together with, as you will see in this lecture, together with looking for dark matter, we're actually, even as dark matter physicists, we are sort of forced to learn about astrophysics, and indeed it's quite exciting altogether. So while sometimes in lab experiments result is, you discover it or not, here you're sure to discover, in astrophysical experiments, you're sure to discover, lots of astrophysics at least, and hopefully dark matter too. Another thing is then, of course, as I will be saying here, astrophysical signals, like what you measure in space, typically does not look anything like dark matter. And then we have to sort of devise all sorts of tools, some of which I will be presenting here. Another issue for looking, when you look for indirect searches of dark matter, is that because astrophysics is complex, and our knowledge is sort of based on, our modeling of astrophysics is based on prior knowledge on astrophysics, we typically sometimes sort of cannot model it properly so far, and have some sort of signal hints. Sort of our astrophysical models cannot explain the data, which then in some cases also presents a sort of dark matter discovery indication. And this is not rare. In fact, so this is old plot, this is old figure, like I think 2015 or so, that sort of lists various dark matter detections that were sort of claimed in the past and how many years they survived. So again, this is 2015. So I think also Christoph was showing in his talk, a range of these dark matter sort of hints that we had in exciting periods in the past. Some disappeared, some were statistical fluke or like instrumental sort of error or fluke as well, and some sort of are hard to sort of prove. They're not dark matter, but appeared very, very unlikely. The Hooperon, as it was called, I don't know if it's still the thing, the galactic center excess that was then already 5 years old, is still around. And in fact, we will be also talking about that. And so then the strategy is, of course, to learn astrophysics and, try to model it, always better, and then look for, try to look for robust dark matter signals, or another one is to look for smoking guns. So to look at features or the signatures that dark matter is not expected to have. And in that case, you work in a background-free environment. And then indeed, if you discover a signal, you can be sure or quite convinced that it is dark matter. Okay, so what I will cover in this lecture, so this is sort of the outline of my lecture, would be first, I will just sort of zoom in the model space of dark matter particles that can be tested with gamma rays, and it was tested with gamma rays. This is again something that you already heard in Laura's talk, at least, but that I will sort of try to put in the more gamma ray context. I will tell you also a little bit about gamma ray experiments, and then as a result of experimental features, what data analysis techniques we typically use. Then something about, so this is again something you heard in Michele's talk, but again here will be a little indirect search twist. I will talk about dark matter targets, again, sort of from a given perspective, about gamma ray astrophysical backgrounds, and then I will give few examples. Like, so the first part of the lecture will be general strategies, how it looks like, and then few examples how we do it in some, in some simple examples, because both of these topics will be covered in their own lectures tomorrow. By the way, I did not mention, if you have any questions, then don't hesitate to interrupt me or to write in the chat window. So about the dark matter model space, as it was, I'm sure, mentioned previously, there are many things that you would like to know about dark matter. For example, is it a particle? How it fits in the standard model, how it couples to it. Then there are questions that could cue us to its nature, because, for example, why it is stable particle? In a sense, stable particles are not many in the standard model, and there is usually some symmetry, like charge in the standard model, that keeps them stable. So some conservation laws. So starting from that, people have built many. Sometimes start to build models of dark matter particles. Then also another cue is abundance of dark matter, because as we know, abundance of dark matter is very close to abundance of baryons. They're just a factor of few from each other, and that is also could be one cue on its nature. Because naturally, if these two sectors are completely decoupled from each other, abundances of both could be orders of magnitude different. Like, for example, between dark matter, I don't know, neutrinos or radiation at this point, and so on. So again, this could be some hint about its nature, and we would really want to know. The hope is, if we discover its nature, that will also provide us a clue, why is this like this, and help us learn more about particle physics for sure. Then, of course, dark matter particles could be composite or elementary. There could be all dark sector, and so on. So these are all questions. This is all the wish list, like the things we would want to know. Of course, before having any signal, we then sort of resort to the simplest assumptions, but should keep in mind that it's not necessary that the simplest reality is the real one. So this is a nice plot from Tim Tate that sort of try to map the dark matter parameter space and its many incarnations, with SUSY sort of here, axions here, little Higgs, asymmetric dark matter, and so on, and warm dark matter, and so on. And so thinking about, so this would be a theorist landscape, and if one thinks about gamma rays, sort of two large categories show up. So this is something that Manuel very nicely presented previously. So basically, there is this large parameter space of something that one would call the WIMP, weakly interacting massing particle, that covers many of the models. And so typically, when you look for WIMP, we just look very generic, perform very generic search, but then ideally, if discovered, it would map in one of these models. Similarly for axions. And then there are other models that are not, that for which gamma rays are not necessarily the best place to look. For example, dark photon, for that typically one looks in lab experiments, or a symmetric dark matter that one goes to stellar evolution, self-interacting dark matter that one looks at small-scale scattering, or warm dark matter, X-rays for neutrinos, and so on. So I just wanted that we sort of notice here that gamma rays are good for a lot of parameter space, but in some cases are, of course, do not have horribly much to say. Again, the orders of magnitude of dark matter models span around of its mass, span a huge range of orders of magnitude. From axions that would be very light particles to WIMPs that are sort of TeV, GeV scale. And then, of course, all these, one goes from sort of 10 to the minus 20 to 10 to the sort of 10 electron volts in this range, from axions to WIMPs, and then one could, in principle, go down to up to Planck scale, to 10 to the 30 electron volts, if one assumes the dark matter is a particle or a field, elementary particle or a field. However, this is not the whole of the story, because dark matter can also be macroscopic, could be primordial black holes, for example, could be some object. So what do we mean by primordial black holes? We mean that from dark matter sort of measurements and detection, gravitational detection, we know that it cannot be baryonic. So the omega baryons is well constrained. So we could not sort of sequestrate baryons to dark matter sector at later times. But primordial black holes are objects that formed from primordial fluctuations, and therefore provide a way to sort of form dark matter before a nucleosynthesis, before the time that we sort of have good feeling of how much baryons we have left in the universe. Sorry. Okay, and so right, so basically there is 90 orders of magnitudes, and we are typically sort of looking under the theory lamppost. So we do have, I mean, it's very hard to do things completely bias free. So we do have typically some theoretical bias when we search for dark matter. Yeah, sorry. So now a little bit about experiments. So the idea. Oh, sorry, it's a bit, I have some delay with my computer. So the idea, no, sorry, I think the one slide is. Okay, I think maybe now it will work. All right, so the idea, of course, as said a few times, is that you have your model you want to test, be it a WIMP or axion, like particles or primordial black holes. And then the idea is that there is in each of these models, there is some way that it couples to standard model. So for example, dark matter particles in WIMP-like scenarios could annihilate to standard model particles, whichever, that could then decay to stable standard model particles that we can then look for. Similarly, for axion-like particles, in the presence of magnetic fields, those convert to photons that we can again look with our experiments, or primordial black holes or black holes in general evaporate to standard model, produce standard model particles in this evaporation that we could also look for. And so focusing now on gamma rays, again, Michele had wonderful lecture about techniques that have been used. And so, as you know, since atmosphere is not transparent to gamma rays, we could either send satellite up there and look at gamma rays directly, or we could look at showers produced when gamma rays hit the atmosphere, and then we can look at those showers from the ground. And typically there are two main techniques. One is imaging Cherenkov light. So this is when you take basically with sort of optical or UV cameras, you look for images of these showers, and then you reconstruct them in order to find energy and direction of initial gamma ray. Or you can look for water Cherenkov light. So when these cosmic rays hit the water buckets of water basically, and then look for Cherenkov light in there. I just wanted to, so again, I will not go into technique, really experimental techniques, but I want to point some features of these techniques that basically determine in part which data analysis techniques we can use then to analyze data and look for dark matter. And so, for example, talking about the Fermi-LAT, which is now a satellite that is now 13 years old, its technology is quite simple, well, at least in theory. So basically, there are conversion foils that convert gamma ray that, when it enters the telescope, convert to electrons and positron, and then we look for electron-positron tracks in the colorimeter. But what I wanted you to notice here that cosmic rays, so the rate of particles hitting, so this is the trigger at Fermi-LAT. This is a trigger rate, it is around 1,000 per second, and actual gamma rays that pass later, that turn out to be actual gamma rays detected, are around 1 per second. And so basically it just makes it very clear that charged cosmic rays, like protons and electrons, especially protons, are at least 3 orders of magnitude more abundant than photons. And so basically what is, from experimental side, what is a tricky thing is to sort of beat down this background of many cosmic rays, say protons, hitting a detector, of which only few, 1,000 are actual photons that you're looking for. And so for Fermilab or for satellites, this is a bit easier task because they have this anti-coincidence sheet, a part of the telescope that basically tags all charged particles that enter. And so with every particle that enter, you have a tag saying this is a cosmic ray, this is a cosmic ray, and so on. And so basically you can define your gamma ray pure sample. Again, in principle, of course, you would need to have huge ejection rate, so things never work perfectly. But you can sort of determine determine gamma ray pure sample to a high degree. And so right. So I think Michael already told you a few things about this, but Fermi was sort of hailed as dark matter discovery tool 13 years ago when it was launched. And indeed, you will see that it's quite a good experiment in at least constrained a huge part of parameter space because of its good coverage, large field of view, and again, a possibility to determine a pure gamma ray sample. So now the full gamma ray range, of course, covers satellites and ground-based telescopes, about which Michele told you much more, so I decided not to go into that. But together, so you see that we managed to cover in this high energy gamma rays sort of from a few hundreds of MeV to hundreds of TeV or so. So basically, Fermi sensitivity is here, and here is the sensitivity of current ground-based telescopes, MAGIC and HESS and Veritas, and then this would be the next generation one, CTA, that would extend it to higher energies with better sensitivity. But why am what I want to underline here is this sort of complementarity, because while Fermilab has large field of view, basically covers 1/4 of the sky, I guess every half an hour, and negligible cosmic ray contamination. Ground-based imaging Cherenkov telescopes, say, are sort of opposite in some sense because they typically have smaller field of view. They really do point towards direction of the sky because it's determined by the size of the footprint on the ground of the showers that you can actually detect, and because you do not have this anti-coincidence detector, you cannot sort of tag which cosmic rays enter. Which initial for showers for which initial particle was a cosmic ray. You can do it again with quite impressive, actually, precision, but it's more challenging because it's not part of your experiment. It's happening up there in the atmosphere. But they do typically have better energy and angle resolution that give them a good significant edge in a number of cases. And so, right, I will also not talk much about water Cherenkov. Again, Michele told you about that. They're in many cases similar to imaging Cherenkov and some to satellite in the sense that they have larger field of view and somewhat worse energy and angle resolution than imaging Cherenkov. And so knowing all this, what can we say sort of about the techniques that we can use to analyze the data? And so for satellites, again, because we do have this pure gamma ray sample. So we know the data that we have, these are actual gamma rays. So our backgrounds in that case is astrophysics and not so much instrumental, not so much cosmic rays, sort of misidentified cosmic rays. And we also have typically large field of view. We have large chunks of the sky that we should analyze. So what people typically do, it's not always the case, but the most standard analysis tool is this template-based likelihood fitting. And so how it works, one basically constructs a model, model of your, so you have your data that you've been, you've been in morphology and energy pixels, and that would be this Nij is the amount of photons that you have in your pixel, Then you make a model of all the components, astrophysical components that you guess that are in your image. This would be the model that predicts then a given number of predicted now photons in each of your pixels, And this model typically contains various astrophysical components. We will talk about this, like what is actually the gamma ray sky. So you will hear from me later what are the particular components. But basically, you split your modeling in as many components as you want. This is the tricky thing, actually, how to do it, as I will also tell you later. And also you add dark matter to your modeling if you want to constrain it. And then you basically construct the likelihood, how likely, how close your model mu predicted counts are to those actually measured by the data. After that, you find test statistics that is defined as a difference from the likelihood calculated given particular parameter of dark matter, if this is what you want to constrain, with respect to the best fit likelihood. And then you defined, so basically, you have best fit likelihood. Here would be, say, dark matter normalization or cross-section. We'll talk about this later. So let's say this A chi is you increase A chi, assuming it was not in the data. As you increase it, likelihood gets worse. Here you get to higher numbers because you define it as a negative likelihood. But say, as you move away from your minima, the likelihood gets worse and worse. And when it gets worse at a given level, then you sort of say, I exclude all the parameters higher than a given value. So this is a bit in a Toulouse language, but I'm sure you got to it in tutorials. And also you're familiar probably with this from your research work. Here, I just wanted to stress that that in this case, so this is a powerful tool. So basically you incorporate doing this analysis basically by splitting your data and models, but by splitting your region of interest in different pixels, different morphology and energy pixels, you basically use all this information, incorporate all this information into your likelihood. So this methodology is aware both about is sensitive both to morphology of your different templates that enter in the model and its energy dependence. And so basically, this is a way to sort of incorporate varying shapes and varying energy spectrum of different components and sort of distinguish them in this analysis procedure. However, on the backside, on the downside is that your results do depend then on how exactly you cook up these models and cook up your machinery. They shouldn't, and in fact, they do not depend horribly, but in some tricky cases, you might worry about that. So it might, the questions you might worry about are your models good enough? Like, am I really representing the data properly, the way I do it? And also how much freedom to live in my in my modeling, because one wants to incorporate all uncertainties, but still to remain to keep some predictive power. So this is typically a tricky thing, and as a result, the systematics, like how like we can always get a result, we can always get a limit or detection, but then how uncertain that result is really depends critically on how good are your models or how much freedom you leave here, or maybe if you have these unknown unknowns or known unknowns, if they're all incorporated here. So we will get back to that then later as we go. Of course, one can always incorporate systematic uncertainties in the likelihood directly in a proper way if one can define the covariance metrics, meaning what are the correlation between various background templates. But that is, in fact, hard to know, and so people do different things, as I will again tell you later. So this would be for satellite experiments. Now, if we go to Cherenkov telescopes, so for Cherenkov telescopes, traditionally a different technique was used. Originally, say a decade or so back. Now this is a little bit changing in time. I will also tell you about that. But the idea there was, okay, first, they have typically smaller field of view, so no need to analyze large chunks of the sky for which binning in different pixels might be really very beneficial. If you have a smaller region of interest, then binning, morphological information, how much you can gain from morphological information via binning sometimes becomes a bit more questionable. Another thing is this significant cosmic ray background. So as I was telling you, it's harder to define the pure gamma ray sample. Like for the events that you have, you think they're gamma rays, but some significant chunk of them are not actually gamma rays. They're just protons that you misidentified. And so having on top of astrophysical backgrounds also the cosmic ray backgrounds, the logic was, okay, so our backgrounds are complex, so let's not sort of model them, because as I was saying here, if you model them, then we are really sort of subject to uncertainties in our modeling, in our sort of bias in the way we model the components. Here the idea was, let's not model them, let's measure them. And so typically they would define a region on where the signal is strong, and then off region where one can assume there is no any more signal, but one can just use it to measure the backgrounds. Both should typically be relatively close by or be sort of meaningfully connected, so that the backgrounds are expected to be the same, but the signal is expected only to be in the on region. And so this works amazingly well when such a procedure can be applied. But the issue is that, for example, for dark matter signals that are extended, it's challenging often to define a proper off region, because some of your signal might be in the off region. And similarly for the backgrounds, sometimes your backgrounds, astrophysical backgrounds here, are not the same as the astrophysical backgrounds there. So in many cases, like this technique unfortunately is not really applicable. Again, exactly because of this difficulty to define a proper off region. And so just keep this in mind. We'll come back to these concepts later. So how about the targets that we typically look at? So what is the signal actually that you're looking for? So the flux of gamma rays would basically be determined by three main sort of considerations. One is how likely is your interaction, okay? So how likely is that you sort of produce standard model particles from a dark matter particle. Okay, so that could be annihilation of two dark matter particles, decay of a dark matter particle, could be conversion to photons in case of ALPS, could be evaporation and so on, of primordial black holes and so on. Then given that it happens, sort of like if a dark matter is converted to standard model particles, how many photons are produced per this interaction? Okay, so this is another thing. This is now, you go to standard model actually physics, saying like I produce a standard model particles, then how many photons I get out of that, initial particles. And the third one is, of course, how many dark matter particles I do have along the line of sight. So, of course, how many particles I do have, then how many of those would actually go to standard model, and then once when they go to standard model, how many photons I'll get. And then if in case of WIMPs, that Francesca will tell you everything in detail tomorrow, one can basically, as you all probably know, rewrite it in these terms. Basically, you have the first term, like how likely interaction is, it's a cross-section, quantifies this quantity. How many photons I get per one annihilation is this factor that can be calculated in the standard model, and then the line of sight. And so given that all these things are sort of being the same, then where do we look? So what are the cosmological places that we will look for dark matter? So this is something that you were already covered in Celine's, Moritz's talk, and I'm sure in others as well. I will just very quickly mention it again through this lens of how we do it in gamma rays. So what matters the most for gamma rays, say. So you all know very well how dark matter is distributed, and then you know that galactic center, since it is the closest to us, is the great target. Then we have the subhalos, the smallest subhalos that is dark, has no bright baryonic counterpart, at least in gamma rays, or also in optical. Like we do not identify the subhalo per se. It's fully dark, but might be a virally independent subhalo. Then we have dwarf galaxies, which are sort of the smallest subhalos that still have baryonic content, that still have stars, and that we can sort of identify their positions via optical surveys. In the Milky Way, we also have these two large satellites, which are large and small Magellanic Clouds, that are sort of the largest of these subhalos that still are bound to the Milky Way. And then, of course, one can go outside of the virial radius, identify close by galaxies in our local group, such that would be Andromeda M31 and M33 Triangulum galaxy, for example, that are the biggest galaxies in the local group together with the Milky Way. And then, of course, then one can zoom out even more to this cosmic web that you also discussed previously, and then localize enormous structures, virally bound, like galaxy clusters, for example, Fornax, Virgo, and so on. Okay, so all these targets are good to look at with gamma rays and have been looked at, as I will also show you later. And then I just wanted to notice that a strategy applied can be different. Like one can either focus on individual targets and do a very good job in modeling exactly that target, its surrounding, and so on, and look for dark matter signal there, or one can look at the samples of various targets. Again, via different statistical procedures, different statistical frameworks to basically then stack or sort of find a common feature between different targets and therefore enhance the signal in some way when looking for a sample of an ensemble of targets at the same time. So, for example, if you look at large scale structure, like say our position would be here, we could look for integrated dark matter annihilation signal in all halos, in all subhalos along the line of sight in different directions. This was one way, for example, that was used, or one can basically cross-correlate tracers of dark matter halos known from, say, weak lensing observations with gamma ray catalogs, and again try to sort of pump up the signal in order to detect it or set competitive constraints. So I believe some of these techniques will be mentioned by Francesca tomorrow. I will not go in detail, but just wanted you to keep in mind that one should know all the targets, and then also maybe think about the ways to combine them together in meaningful ways to increase the sensitivity of the search. But of course, the elephants in the room, again, discussed as well previously, is that we do not know very well the distribution of dark matter particles on small scales. So this has been also covered in a series of lectures previously. And it does have a significant consequence for dark matter search and gamma rays. So let me just briefly recap those issues. So in terms of n-body simulations, which was covered, say, in Gustavo's talk, especially, is this limiting, they have limited resolution, of course. And so even though they all, as again was said previously, cover find self-similar dark matter. So this is dark matter density as a function of a radius from a halo center. So typically NFW or ANAS profiles, self-similar solutions independent on halo size are found in dark matter only simulations to describe all halo sizes. But of course, this all works down to distance, the resolution of your n-body simulations. They all agree outside of your resolution range, but of course at small distances that then basically dominate your gamma ray signal, which, for example, in case of WIMPs depends on density squared. You become, quite uncertain because you have to extrapolate what you find outside of the region of interest. And so again, like, it's impressive how well N-body simulations do and how much we know about dark matter. But then, of course, it's always up to certain point that we then have to, be quite, careful about when we do the analysis. Similarly, for small masses, for halos of small masses, because also there we detect the smallest subhalo size mass in simulation is set again by its resolution of simulation, which we know, which of course has nothing to do with the physically smaller scale of subhalos that dark matter develops, and could go as low as 10 to the minus 6 solar masses for WIMPs, say. And again, here is a big discrepancy and big extrapolation that we should do. And so again, always something to keep in mind. And many people are working on that, as you heard, and it was discussed in the first part of the school. Another thing, of course, when one talks about limitations of simulations, of course, are variance. So Annalisa also gave a wonderful lecture yesterday talking about these challenges, because dark matter, at least it's simple to simulate because it has only gravitational interactions. But then if you want to include variance whose feedback actually could be critical on those small scales on dark matter density, then it becomes extremely challenging to do it properly numerically, because you have to cover a wide range of scales. You have to go from, interstellar medium and stars, basically stellar feedback, all the way to, AGN feedback and, cosmological evolution and so on. So it becomes really a formidable problem, and it's impressive what simulations do today, that they're capable of producing all these realistically looking galaxies, tracking magnetic fields, cosmic ray distribution, and so on. So this is really a growing field, and we're learning always more. However, of course, it's still in progress. So there are still open issues, and something that the uncertainties that then necessarily just propagate in our limits or in our sensitivity projections when we look for dark matter and gamma rays. And then one can say, okay, we cannot predict it very well, but what can we say from observational side? So maybe we can just look at tracers of gravitational potential, and from that determine dark matter distribution, which of course is not easy. It's arguably might even be harder. And so, talking about the smallest halos, I just wanted to show you here this figure that shows a bright. So these are the smallest objects sort of in the galaxy. Those would be dwarf spheroidal galaxies, satellites of the, say, Milky Way or a galaxy, and its globular cluster population. Okay. On this axis, it's plotted brightness, which basically correlates with number of stars this we can observe from these dwarfs or globular clusters. And on the x-axis, it's size in radius of these objects. Okay, and so you can see right away that while some dwarf galaxies are much brighter than globular clusters, some could be also much fainter. And in fact, there is this like sort of region where it becomes actually very hard to tell a difference between globular cluster and a dwarf spheroidal. And why there is this big range of radii in difference between the two. So the idea is that dwarf spheroidals are extremely dark matter dominated objects. So they could have hundreds of stars, but their masses are 10 to the 8 solar masses or so on. So those could be extremely dark matter dominated dark objects, and large dark matter gravitational potential keeps the size larger, because the stars are simply living in a deeper gravitational potential of dark matter. For globular clusters, we believe that even though the number of stars in globular clusters is comparable to that in dwarfs, they're typically much smaller, and that is because we believe that these systems do not have dark matter, a significant amount of dark matter. The idea is that maybe through mergers or through evolution, the outer parts of dark matter halo were stripped, and sort of they are left with maybe tiny dark matter cusp or small amount of dark matter in the very centers, but not necessarily large amounts of dark matter. And so I'm just showing this also to illustrate the fact that while we have so-called classical dwarfs that are quite bright, have a lot of stars, again, brighter than globular clusters, significant population of dwarfs are these ultra-faint dwarfs, where they basically are very, very faint, and becomes very hard to determine, say, physical extent of these objects, and also then the gravitational potential due to dark matter. So basically we have these classical dwarfs, then, ultra-faint dwarfs, and then below some mass range, say 10 to the 8 solar masses, we have no any more observational knowledge, because simply smaller halos do not host significant amounts of gas and stars. And so again, this was Céline, for example, went through this, how one can use the spherical Jeans equation to relate the velocity dispersion of some stars that we measure, and to predict the total amount, this integral so-called J factor defined here, that determines then your dark matter signal. Again, I'm just saying this again to say that yes, we can use stars to determine dark matter content, and for classical dwarfs we can do it quite well, but then we start to lose sensitivity as luminosity of these objects fades, and we cannot simply go smaller than a given subhalo mass. Similarly, for small distances, in a big galaxy like the Milky Way, we can, outside of the inner few kiloparsecs, we can very well determine the dark matter content, because we can measure, say, rotational velocity of stars, of gas, and so on. There are some uncertainties, but they're rather under control. But in the inner regions of halos, the gravitational potential, as you see also here, is baryon. So this disk and gas basically dominate the gravitational potential, and here it is very hard to say how much dark matter you have. And so basically, right, that's that, as I was saying before, we are both n-body simulation and observationally limited in some small scales. I just wanted to note, in terms of gamma ray searches, so to sort of, that you should keep in mind that if you are looking at the objects from outside, say like looking at dwarf or some small objects that you really sort of observe from far away, that you cannot resolve in the regions, then what you more care about, you're more limited by your not knowing its properties of its subhalo population, like the total mass, like the total J factor of the object itself, or how many subhalos it has, and so on. However, if you're looking at centers of halos, or if you can resolve the inner regions of your dark matter halo, then of course your uncertainty is mostly dominated by not knowing exact dark matter density profile of those objects. So while if you look at the dwarf galaxy, say from outside, you do not care so much about which profile is, in the inner regions, because you're dominated by the overall J factor outside. Your gamma ray signal is dominated by the overall J factor. If you look at the galactic center, say, then you do care a lot about what is exactly the shape in the inner regions. Okay, so now we talked about, experiments and analysis techniques. Where do we want to look at? And now let's look how gamma ray sky looks like. So what are the astrophysical backgrounds that we have to deal with? I guess you can go ahead. If people are up for having a very short break, we could also take it now. But if nobody objects, I would continue. But if you feel like having a break, just let me know. No problem at all. Okay, so how does the Fermi? So first we'll talk about the Fermi or the GV sky. Rather, I should have probably titled it the GV sky. So the GV sky contains basically three main components. One is this emission from the galactic plane, Okay, so this is galactic sort of emission coming from our own galaxy that is sort of looks diffuse. It's large scale. Second component are point sources. As you'll see, of course, there are always gamma ray point sources on the sky, and we will talk about this, like the nature of these point sources. And then there is isotropic emission. So basically, if one looks at high latitudes, it's not that there is sort of, one does not arrive to zero gamma ray emission, but one observes actually a net monopole, basically isotropic, significant isotropic signal coming from everywhere in the sky, for which we believe it's extragalactic in origin. I will also tell you more about that. But let's now talk about this diffuse emission in our own galaxy. So basically, this diffuse emission from the galaxy itself is the dominant component. And basically, 90% of, say, of light photons in GeV energies come from the plane. Because you can see it's much, even though its volume sort of on the sky, its fraction of the sky is much smaller, it's much, brighter, okay? And where it originates, so Daniele will tell you all about it. But in a nutshell, due to the magnetic fields of the galaxy, the cosmic rays that are produced, say, in supernova explosions or in different pulsars, in different acceleration processes in the galaxy, remain basically confined to the galaxy for millions of years. Okay, so they just do not just like once produce escape, but they just remain confined in the galaxy. And while they diffuse and move diffusively, and while they diffuse throughout the galaxy, they produce gamma rays in variety of processes. And all these processes, of course, then accumulate in this bright gamma ray emission, diffuse emission that we observe. So what are the processes? Again, something that Michele also was telling you about. The three main processes that contribute to this diffuse emission in gamma ray ranges are the pion decay. So the protons in the interactions with gas produce pions, and pions decay to photons. So this produces majority of emission. Again, this statement is an energy dependent, but in a ballpark above GeV or so. Then there is also Bremsstrahlung emission. So this is pion decay is a process that happens with cosmic ray protons interact with gas. When cosmic ray electrons interact with gas, they produce so-called Bremsstrahlung emission due to the acceleration in the electric field of atoms of a gas. Okay, and so as you see, both of these, while they have different cosmic ray particles responsible for this emission. In pion decay, it's protons. In Bremsstrahlung, it's electron. Both sort of as target need gas. So in order to happen in any of these emissions, you need gas particles. And that's why the morphology, the shape of pion decay and Bremsstrahlung emission basically follows gas. That you have gas, you do have this emission. And so this is something that one can then use in the analysis as a tool to sort of distinguish this astrophysical emission from say, your signal that you're looking for. Another emission that is also present, and in fact it's quite tricky, it's inverse Compton emission, because your cosmic ray electrons can upscatter. So in this case, you know that galaxy is also infused with low energy photons. It has optical photons, infrared, and so on. Because of stars, it's full of stars that produce their own thermal emission and produce photons. Okay, and then electrons, these highly relativistic cosmic ray electrons that we're considering here. So these cosmic ray protons and electrons that can produce your GeV gamma rays typically have TeV, hundreds of GeV energies, and those when they interact with low energy photons can upscatter those low energy photons to high gamma ray energies. Okay, so this is called inverse Compton emission. And basically you see that in this case, you have much less handle on its shape, on its morphology, because while here we said you'll in order to have pion and Bremsstrahlung emission, you need gas. So without gas, you don't have it, so you know how it looks like. In this case, you basically need to, here the target are low energy photons. So you need a very good modeling of your, diffuse light in the galaxy. That is actually quite tricky because it's hard to measure. It's also very hard to model because it involves all the, stellar processes and so on. And so this emission is sort of, morphology is much less constrained. But you see here already, in order even sort of conceptually like this, to describe this emission, you see that you need many things that determine it, because you need to know cosmic ray proton and cosmic ray electron spectra in the galaxy. You need to know gas density in the galaxy. You need to know low energy photon density in the galaxy. You also need to know magnetic fields, because electrons, that they would necessarily lose also energy in synchrotron radiation in the galaxy. That even though it does not produce gamma rays, still changes the spectra of cosmic ray electrons and so on. And indeed, if you want to sort of solve and predict this gamma ray emission in the galaxy, it's extremely complex process. Again, that Daniela will have the whole lecture on that. You need to know many parameters. You basically need to solve the fusion equation so this is the density in real and momentum space of cosmic ray particles and how it changes in time. That depends on many parameters, depends on sources, depends on diffusion properties, on convection, on energy losses, sometimes on fragmentation if you're considering higher atoms as cosmic ray particles and so on. And so it is hard. Many of these parameters that are needed are huge, have significant uncertainties. Luckily, we have sophisticated numerical solvers, such as Galprop, Dragon, Hermes. You will have tutorial on all of these, on Dragon and Hermes. So you will learn all of these details. Again, these are tools that have been on the market, I think, for a decade or more now. And so in time, as we got more data from astrophysical observations, they also got much more sophisticated. And so similarly to N-body simulations, it's amazing what the field has achieved. For example, now, while before all this diffusion and description of a galaxy was treated as a simple cylinder with not much detail, now 3D gas distributions, 3D interstellar radiation field with low energy photons are implemented. For example, time-dependent cosmic ray source distribution that now starts to take into account, because all this diffusion equation solution is typically done in a steady state, assuming that one has the stable population of cosmic rays in the galaxy. However, that is also a simplification, because we know that sources sort of have their time span, and they have a sort of period over which they inject electrons, and that the spectrum of electrons, for example, the protons, changes over time after that, and so on. So basically, it's very complicated. Numerical codes are catching up, very quickly to whatever we learn, to the things that we are learning about the galaxy, and to the precision of experimental data that we have now. But it's important to anyway, again, take all these uncertainties into account when one looks for dark matter signals.
Excuse me?
Mm-hmm.
A simple question. I didn't understand. What is LAT photons? What does it mean, LAT?
Sorry. Yes, thank you. I was going too fast. So, right. So for me is a satellite, as I was again saying before, and covering this GeV to hundreds of GeV energy range. No, in fact, I'm saying it wrongly. For me, is a satellite, but satellite itself, has two instruments on board. So one of them is LAT, which means Large Area Telescope. And so basically, all the things that I will be talking about here pertain to the Fermi LAT data. So because Fermi, as a satellite, again, has also another instrument that is called Gamma Ray Burst Monitor, GRB monitor, and and this is a different instrument, different collaboration, covers lower energies and so on. So when I talk about Fermi results, I always talk about Fermi lat results. And so sorry that I got into slang here and, sort of exchange this thing. But basically, whenever I say Fermi, I mean Fermi dash lat, because I'm only talking about one instrument on Fermi satellite.
And so the 90% of those photons you said that are produced via these three processes, like
Yes.
3 slides before?
Yes, exactly. Yeah, thanks, Sebastian, very much for interrupting, because sometimes, when one works in a field, then sometimes, uses acronyms and things, without defining them. So please do again if I get there, if I go there. So basically, these are the three main processes that produce. So maybe I can just go, so I did not put it here, I'll go back, but basically, so this would be the spectra of those. So for example, this is from sort of 100 MeV to 100 GeV. This is the spectra that you would expect from pion decay. Okay, it usually has this shape of a pion bump. This is because of the mass of the pion, basically. This emission falls down below 0.5 GeV or so. An inverse Compton emission that is typically harder. Okay, it's a power law as well. And then Bremsstrahlung is the third kind of emission, and that one dominates here around 1 GeV or so. So typically cuts off significantly above 10 GeV. So it's important if you look at GeV energies, but sometimes it's neglected at high energies. And as you see here, this pion decay is by far the dominant one. Again, it's energy-dependent statement because at highest energies, inverse Compton can dominate. But in these tens of GeV range is the dominant one. Okay. And all these, so I will show you later, but we can basically, via these numerical solvers like Galprop or Dragon Hermes, it's amazing, but so as input they have the gas density, the interstellar radiation field density, the cosmic ray distribution, cosmic ray sources distribution, and so on. Now you have to make tons of assumptions of how, because all you have is basically this image here and measurement of cosmic ray protons in electron spectra at Earth. I will mention this later. So you know how cosmic ray electrons and protons look here, the spectra, and then how gamma ray sky looks, just 2D image like this. And then you have to reconstruct back and sort of, assume along your line of sight where you look at how many cosmic ray sources you have, what are their diffusion properties, and what are the targets in which they lose energy. And then all is codified in equations like this that are then solved numerically. And they do a very good job. So basically the images that we get are very similar to this. In fact, here I wanted to show it. So sorry, I'm going back and forth, but if you subtract, so if you make the best model that you can, like Galprop, say, and Dragon, of this emission, okay, and then you subtract it from the real data, you get quite good description of what is happening. So this would be residual. This would be what happens after you subtract the two. It's in percentages. So like it's 30%, goes up and down 30%. So you see that more or less you describe the sky quite well with the codes like this. So these were residuals in 2012. Now you can get a bit better than this, but I wanted just to illustrate the point. So you see, if you simulate the sky, then you subtract it from the real data and normalize, you then see that you can describe sky up to 15% on most parts of the sky. So you get there. It's actually quite amazing that such complicated processes can be actually modeled quite successfully with 10-15% uncertainties. But you see that anyway you fail in some regions. You have up to 30% uncertainties because maybe you underestimate the gas density, or there is some particular structure in the sky that you're not taking into account. You see in the plane you fare worse than at high latitudes and so on. So Daniela will go in all details about this, but it's really how should I say, fascinating, the achievements, and also fascinating what we learn about our galaxy by measuring gamma rays together with cosmic rays. But now focusing on dark matter search. So why is all this important for dark matter search? I mean, it's sort of obvious, but what is the trick here? The trick is that for dark matter signal, as you know, and you've seen also in other lectures, is quite bulgy. Like we expect it not to be a single point in the center, but to come from all the inner region of the galaxy, gamma rays from dark matter. Okay, say in the case of especially beams, but whatever dark matter is, if it produces dark standard model particles or gamma rays in our galaxy, the signal should come from a larger region. So it should be bulgy, diffuse, and in fact, also this diffuse emission or this interstellar emission is diffuse, and so it becomes very tricky to distinguish between the two, just based on this simple sort of reasoning. And then, as I was saying, showing you previously, these residuals, that you can model this emission impressively well, but there are imperfections for sure. And then, you have to be very careful that, because some imperfections say here, you say, okay, this is some astrophysics I do not know. But some imperfections here, then you might think, oh, maybe I discovered dark matter. So you actually have to be extremely careful and to quantify very well the true uncertainties in your modeling if when you look for dark matter. And in fact, I was showing also these early sort of residuals when you subtract the model from the data, because already here you can see that there are large structures in our galaxy. Again, Michele was talking about these Fermi bubbles that were discovered by Sue and collaborators in 2012. Basically, by playing this game, modeling the data, performing this likelihood analysis, template likelihood analysis that I described before, and subtracting then your best fit model from the data, basically people realized, first of all, that there are actually diffuse signal in the center of our galaxy, but it's not dark matter. These are those Fermi bubbles. And so this is another issue then, because you do already have this diffuse emission that it's hard to model. On top of it, exactly near the galactic center where you want to look for dark matter, you also have Fermi bubbles that are fainter, but even harder to model because we do not know their physical origin. Because for cosmic rays, at least you have physical picture how it should all work out. For Fermi bubbles, it's still highly unknown. And so all this, of course, is a big challenge for dark matter searches in our galaxy. And then, as I was saying here, also spectrally, astrophysical emission is a power law emission. So pion emission, inverse Compton emission, they are all sort of power laws. Dark matter emission is also power law. It's sort of on this E square, when multiplied by E square, it's sort of you can see more clearly, it's sort of a broken power law. But if signals are faint, sometimes it's not also trivial to distinguish. So unsurprisingly, it is challenging. Then moving on the list of gamma ray emitters, there are point sources. So point sources, there are actually amazing number of them in GV energy. So again, I should call this the GV sky. So in 4FGL catalog, it is 8-year catalog, there are more than 5,000 sources. And since significant number was added, and so it's really wonderful that now we have all these sources to sort of study individually, understand source properties, and so on. So just by looking at the census sort of these sources, we see that the biggest chunk are extragalactic. Okay, this is of course obvious also because of the fraction of the sky, that does not come from the plane. And then, and most of these sources are AGNs, these active galactic nuclei that are the brightest extragalactic sources. So these are the supermassive black holes in other galaxies accreting material and producing jets and extremely energetic particles in gamma rays. And those have subclasses. And the most numerous subclasses in gamma rays are so-called BLX and FSRQs. The two have different spectra and different sort of redshift evolution. So we are starting to learn basically all these things thanks to this very rich data sets that we have now. And again, are things that one also needs to take into account if looking for dark matter in extragalactic emission. And then there are star-forming galaxies. So AGNs are these galaxies for which the black hole region is much brighter than the rest of the galaxy. They have extremely active black holes. Other so-called star-forming galaxies are galaxies that you can see basically detect emission from the galaxy itself. The black hole is quiescent, not so active, and so you can detect this emission from the disk, sort of, as you believe from the disk. Like these are galaxies similar to the Milky Way, and few were observed among them: LMC, SMC, M31, M33. Okay. Among galactic sources, on the other hand, the pulsars are the most numerous. So these are these red points. You see them a lot on the sky. And then there are some other sources that less numerous on their own, that, such as pulsar nebulae, supernovae, which are also in many cases extended sources, globular clusters, and so on. What I wanted you to notice here, that about 1/3 of the sources, this number maybe got a bit lower in the latest catalog, but about a third is unassociated. So about a third of those sources we actually do not know, we cannot be certain what is their origin. So for sure, a large chunk of those are either AGNs or pulsars, but some new source populations, some new source classes could be hiding there. And this is where one looks also when one looks for dark subhalo signals. So those would be sort of the most interesting one for dark matter search. I just wanted to stress, even though Michele told you about this, is that due to this Fermi and Agile data at the GeV energies, we now have this like sort of revolution. Again, not so many sources were known pre-Fermi and Agile. So this is the first time sort of that we have so many sources, so many gamma ray sources known and detected. And as a consequence, for example, we discovered these many AGN subclasses and in gamma rays, and also, for example, have this first hint that neutrino might have been observed from a jet of an AGN observed also in gamma rays, say. So this is sort of arguably less relevant for dark matter, but more relevant is that in our own galaxy, you see these are days into the Fermi mission, the measurement of Fermi lat, and you see the numbers of discovered pulsars. So at the beginning, few gamma ray pulsars were known from egret measurements. So this is a precursor to Fermi and Agile. But then Fermi and Agile, while in orbit, they started to discover huge numbers of these pulsars. So here at 2,000 days, 50, 60 were known. Now we're at around 5K days and around 250 pulsars are known. So basically from handful, we arrived to hundreds. So also now we're learning a lot about how numerous these pulsars are in gamma rays, and then about their properties and so on. And another important thing is that there is a class of pulsars called millisecond pulsars that was basically sort of speculated pre-Fermi, but now we have many of those as well. So this will also come up in what I will say later, because those indeed present a formidable background for dark matter searches in the galaxy. And the last sort of template or emission component is this isotropic emission. So as I was saying before, if you look at high latitudes, you do not arrive to sort of zero gamma ray emission, but you can measure this beautiful spectrum that goes of hundreds of MeV up to hundreds of GeV, up to actually 800 GeV or so. So you have this sort of power law with a cutoff at high energies. And then the origin of that is amazing. So where does this come from? So you have these gamma rays coming from, the space from extragalactic, so we know it's extragalactic because it's isotropic. It does not correlate with the plane, but because we just see it as a diffuse emission, not associated with a single source, we actually do not know its clear origin. And so in part, for sure, the fainter counterparts of this sort of the bright AGNs we observe as power source point sources, but the faint ones will contribute to this isotropic emission. but still also maybe some dark matter signal might be hiding there. And I think also that you'll heard or will hear it here in the school. So how about the TV sky? So this is all happening in gamma rays, and I was saying what I was showing was mostly about Fermi-LAT, but also Agile made a significant contribution to these discoveries. Here, if you talk about the TV sky and the counterparts, what we know about this diffuse emission, what we know about point sources, and then this isotropic emission so far is not constrained and probably won't be because, or it's very challenging to be. I mean, people are also working on sort of detecting this in different ways. But the point is that they have smaller field of view and this higher cosmic ray contribution. So just by measuring it like this directly is impossible. Again, if one devises smart techniques, it might be actually possible to detect it. Yeah, for now, we will not mention it. About diffuse emission, this emission induced by interstellar emission induced by galactic cosmic rays and proton population. Basically, it is again harder to measure because, as I was saying, it's smaller field of view. So what experiments did are, say, for example, Hess did a galactic plane survey. So because, again, you detect small portion of the sky, but then if you observe it in a survey mode, like do observations along the plane, you can sort of accumulate the data, and basically this is what was measured. Okay, so here is what was measured, and here is sort of the exposure that then necessarily was sort of ununiform across the galactic plane. But from this observation of the galactic plane in this way, there are indications that actually counterpart of this diffuse interstellar emission at TV energies was detected, even though its properties are not clear, very much constrained. One thing I wanted to mention is that where in one place where diffuse sort of large scale emission that correlates with gas distribution at TV energy was discovered is the galactic center, of course. It's called the galactic center reach. So it was discovered by Hess. So this is a region around 2 degrees. You see around the galactic center and around 1 degree, less than 1 degree thick. It's diffuse, large scale, it correlates with gas. So we believe that this is this sort of emission by proton population or some gas related emission. Of some processes related to gas, to energy losses in the gas. And this would be the spectrum. So it's extremely hard spectrum extending to, several tens of TeV. And so obviously so if you measure gamma ray emission up to tens of TeV, that means you must have protons up to even a PeV that could produce such emission when scattering on gas. So this was amazing discovery that is sort of illustrating that we have galactic cosmic resources that produce PeV like protons and electrons that then produce this sort of TeV emission. However, we still do not know it. If you look around the plane, it's still poor. So only in the galactic center it's clearly measured. Elsewhere, it's detected, but its properties are still not easy to pinpoint. Then point sources. So again, at TV energies, as Michele was showing, the flux of sources drops significantly. So it's much harder to measure the sources. And again, if you have small field of view, you have to observe at a given position. So you do not have this like full sky coverage as it comes for free for Fermi, for satellites. And so several hundreds of sources are known now in TV energies. They're again AGNs, mostly at high energy, among extragalactic sources, and sort of pulsar V nebulae or supernova remnants in the plane. A very important discovery was made recently in the HAWK data, in the water Cherenkov telescope HAWK, when they measured not only the pulsar V nebulae. So basically what is in the astrophysics of this is that you would have a pulsar in the middle that produces electrons and positrons that then sort of shock in this pulsar V nebulae region that you observe then as a TV source as those electrons lose energy here close to the pulsar. What was then discovered that there is even larger region in which electrons are sort of confined and scatter with a diffuse in with diffusion properties, somewhat different diffusion properties outside in the galaxy. So all this is probably too much sort of astrophysics for general purpose, but I just want to say that progress is rapid because such measurements can then help us really understand much better this cosmic ray electron, say, emission at a source. Well, for now, we sort of guess and do some phenomenology around. We might actually be able to actually measure how many electrons are injected by these objects, what are the diffusion properties around the source, and so on. So it's hard, but progress is happening. Big steps is almost on a yearly time scale. And so now to summarize also this part, so what are the main challenges in looking then in gamma rays? So basically you have these complex astrophysical backgrounds, you have dark matter distribution that is not perfectly known, it's another big unknown, and then you have instrumental limitations that you have to sort of take into account. So for example, and also of course, backgrounds and problems are target dependent. So for example, if you look at the galactic center, then your main astrophysical background is this interstellar emission that we discussed before. And your dark matter distribution unknown is exactly how the dark matter distribution changes with radii. While if, for example, you would want to look at dark subhalos, then your astrophysical background are these unassociated sources, point sources, and your dark matter unknowns are the distribution of like how many subhalos you have of a given mass, how concentrated or what is their mass distribution, and so on. So one then thinking about particular target and about particular strategy, then one goes back and looks what would be the backgrounds, what would be the dark matter distribution unknowns. Okay, again, looking for smoking gun is always an issue. A good choice. Trying always to think like, can I somehow, for my model or for my sort of target, can I have some clear-cut smoking gun signature? Or if not, then I would have to deal with all these uncertainties and then also verify them elsewhere to make sure I'm getting things right. And so now we finally come to a few examples in the last 20 minutes or so. And I wanted to tell you, so time permitting, we'll see about 3 examples. So one would be for WIMPs. One would be, again, this dark matter detection in the galactic center region, this galactic center excess, because this gives good lecture, like it's this very complicated region, everything that could go wrong in terms of backgrounds goes wrong and so on. And so this is sort of a case study, like how one of the hardest things that, and the messiest things that you could do in this field. And so it's a good point for illustration, at least. Then in terms of axion-like particles, I wanted to discuss example of one smoking gun signature that one could look for. And then if you get to it in terms of primordial black holes, gamma rays were actually extremely powerful to constrain a part of parameter space. I just wanted to mention that. Again, if I have time, because in this way, so WIMPs will be discussed by Francesca tomorrow and also by Manuel. And so I did not want to go into much details in any of these, but just to give you the big picture. Instead, I'm talking about this galactic center excess, which I realize is also a darling example of the school, because I noticed also other lecturers took it as a case study, but for a good reason. So talking about WIMPs, so just first few, a bit step back and few sort of big picture comments. So if one looks sort of a state-of-the-art limits, thinking about all indirect detection messengers. This is the picture. So this is something that Michael Cirelli showed and token apparently will soon appear. So here you would have annihilation cross-section that is constrained. And here you would have dark matter as a function of dark matter mass. Then of course, the holy grail, like what you usually want to reach, is this thermal cross-section. Okay, so this, I'm sure that you already are familiar with what is a thermal cross-section. I think that probably Laura explained how we get to that in her lectures at the beginning. So this is basically the cross-section value sort of predicted for vanilla WIMPs. So this is something that we sort of set ourselves as a goal to probe. If you have any questions or it's not clear what I refer to this, please just speak up. I'll be happy to explain. And then, and then if you look at the strongest limits, the ones that really do cut into this, come very close to this thermal cross-section or cut into it, you see that gamma rays are actually excellent probe. So the solid lines are gamma rays, and you see that some of the strongest constraints are given by gamma ray dwarf satellite limits or by Hess observation of the galactic center, say here. Antiprotons, so cosmic ray antiprotons, I will tell you a bit more about that, are also quite strong, and those would be those sort of red and blue lines here. And then you go to CMB and other probes that we will not discuss here because neutrinos and so on, because anyway, gamma rays are the topic of the school. But I just want to say, so gamma rays, indeed are a very powerful probe and play a very critical part in this all this indirect detection landscape. If you then zoom in on various gamma ray analyses, again, you see that unsurprisingly, dwarf satellites provide very strong limits, but then you have a variety of various techniques. So this is something that I was mentioning before, that you could look either in a single target, or you can do cross correlation, look at the isotropic flux, do various things to search for dark matter signal, elsewhere, and they all are worse than dwarfs, but not by huge factors. So the idea is that if signal is observed in dwarfs, we should be able sort of to test it then by smart application of other techniques. And as I said, then in all this landscape, what I wanted to focus on are these few sort of detection hints, the so-called galactic center excess, because as you heard also in other lectures, if you look at the center of our galaxy, there is much harder to set limits to constrain dark matter, because there is a signal that actually looks too much like dark matter, that sort of remains as a sort of a signal hint that we are still trying to figure out, could it really be that, or it's a background unaccounted for. Sorry. And so how would such analysis work? Again, I mentioned this before. So first you choose your region, you take your data, you choose your region of interest where you want to look, and people usually take 10, 20, 30 degrees around the galactic center. You don't want too small, because larger region allows you it's typically better. I mean, you get, it's positive, of course. There are pros to taking a larger region, because in this likelihood procedure that I describe you, that works in such a way that you bin your region of interest and then sort of incorporate all this morphological signal in your likelihood. For that reason, if the region is larger, you have more power in the analysis method to constrain also astrophysical components, because if you focus too narrowly in the region where your signal dominates, then the confusion between signal and the backgrounds is larger. So typically 10, 20, 30 degree region is taken in the fast analysis. And then you have to write your model. So what astrophysical components then you want to take into account here? And of course, as we've seen before, you need to take interstellar emission. You have to have a model for that. This is the brightest component. Then you have to take into account the point sources. You also should take into account isotropic emission, even though it's subdominant in this region. And turns out also the Fermi bubbles are there, so you need to model them somehow. Even though they're quite uncertain, people do guess, have to sort of introduce this template as well. So devil, of course, is in details, and that's why this also galactic center excess that we'll talk about is remained controversial for many, many years, because it really depends how you do it. Like, what do you put, how do you approach, even philosophically, this, how you build your models, and then how many free parameters you leave in your, in your fitting procedure. For example, there are sort of two maybe main philosophies that emerge. One is to sort of build a physical model, in a sense, use what you know from cosmic ray observations, from independent observations of gas and so on. And so you build a model that you say, look, I believe independently of gamma rays, I just believe this model is correct based on all other assumptions. And I put in that model in my likelihood procedure, and I get some result. Then if I want to estimate uncertainty of that, I sort of then vary slowly assumptions in my physical model and always repeat procedure and get sort of different maybe result to some degrees. And then this scatter of results illustrates sort of my systematic, my real uncertainty in my modeling. So this would be one way. Or sometimes people just take a model very general and allow lots of freedom to it, allow the model to adjust. They say, okay, I do not know gas density better than 20%. I do not know this better than that. So I sort of allowed lots of freedom to my initially physical model, but then allow it a lot of freedom to adjust, still applying some priors, allowing it to adjust, but not as much as to sort of absorb dark matter signal. And so this is also what people do. And so, for example, a good example of this taken to the, taking the full advantage of this sort of philosophy is a code swordfish that maybe also Francesca will tell you more about. Okay, and so by applying various incarnations of such techniques, this galactic center excess emission that cannot be explained by these input models emerged. So it emerged already, 2009. So in the first analysis, together with, by Hooper and Lisa Goodenough. That's why it was this Hooperon in one of the first slides. So 2009, it's a long time ago. And so at the beginning, it was not clear, is it maybe systematics, is it really robust and so on. But in times, many groups repeated analysis, and it seems it's robust. So as you heard in other talks, it has dark matter-like spectra and dark matter-like shape, and that's why it was claimed initially, and still possibly dark matter is one of the valid explanations for this success. What I wanted to show here, so this is one of the latest analyses by Di Mauro, 2021, the black dots. But this also plot, so this is a spectra, what was found, the flux of this galactic center excess emission as a function of energy. And you see that like this gray, this yellow and blue and so on bands, they all show estimates on uncertainties in different analyses. And you see that some analyses just give, the data points that they have statistical uncertainty. Some really do a careful job of trying to implement all systematics, even the orange one here, really, this was the Fermi-Lat collaboration work from 2017. They tried really to allow all sorts of freedom, like use alternative gas maps, include additional sources in the galactic center of electrons, vary the Fermi bubbles template, and so on. And so, bottom line, uncertainties are large, but this galactic center excess anyway seems to survive. It seems it's really there, some emission that is not modeled in these traditional ways. And then what it can be due to, so this you heard many times, it could just be dark matter. It could be your, vanilla WIMP. It would be something like around 100 GeV heavy with sort of thermal cross-section and NFW profile, almost, standard one. And so this is something exactly that you would think, how you would think dark matter would look like a priori. So that's why all the excitement about this. But also then we were talking about these pulsars that have been discovered now by hundreds in the galactic plane, unfortunately have very similar spectra to this galactic center excess. And so this is the story, many fancy or like people tried really different ways to try to get to the bottom of this. And of course, it's hard to, at this point, it's hard to say for sure, but pulsars are quite motivated and there is no reason. One cannot be sure it's dark matter for sure at this point. And so what did we say before? So if you have a detection, then, and it seems robust based on that target in your analysis, you must then do multi-target and multi-messenger cross-checks. Like, is this the signal? If it's true in galactic center, I should then see it in other targets and with other messengers. And indeed, the thing sort of is interesting also in this respect, because, for example, one can look in the direction of Andromeda. This is our sister galaxy, and indeed one can observe gamma ray emission from the bulge of Andromeda that would correspond to sort of this bulge emission from the galactic center excess from our own Milky Way. And so far, it seems that that also from M31, we see sort of extended emission from the bulge, which sort of is consistent also with pulsars. And so it might be that pulsars are indeed, so here in the Milky Way, what we would predict for pulsar flux and what we observe based on some models sort of coincides, and indeed it's reasonable that this is pulsar emission in Milky Way. And similarly in M31, it could also be the pulsars that we observe there. So this is just, but here I wanted to illustrate that looking at maybe in other galaxies that is close by to us, you could learn, in its own bulge, we might hope to learn more about the bulge environment of our own galaxy, because our own galaxy, it's much more complex system. There we see it, the bulge we see from side on, and so in some cases, in some sense, it might be easier. Other place where we want to check if this galactic center excess discovery is indeed true is dwarf galaxies. And indeed, it seems that because we do not see the signal in dwarf galaxies, and knowing how much dark matter we have in dwarf galaxies, it might seem that the galactic center excess is excluded. So this would, for example, put the end on this story. We could say, look, it seems there is dark matter in the galactic center, but we do not see it in dwarfs. And since we know how much dark matter is in dwarfs, it's excluded. It cannot be dark matter. It must be pulsars. Unfortunately, it's not so simple, because all these uncertainties on dark matter distribution, as I was telling you before, you have few stars whose motion you can measure, you can detect and model, that you can use to constrain dark matter distribution. And it turns out, if you play a different game, if you do analysis of your dark matter distribution, it works differently. You can do it in motivated ways, and as a result, the limits from dwarfs could become much weaker, significantly weaker, so in such a way that they do not exclude the galactic center excess, the dark matter explanation of the galactic center excess. So looking in gamma rays, galactic center excess we cannot exclude that it's of dark matter origin, say. So doing multi-target did not help us much yet in this sense, like not yet robustly.
I'm sorry?
Yes.
What would be the mass of the dark matter around?
So that depends, right? So that depends which channel you assume. I think this is it's assuming BB bar. So this is you have to assume a little bit to remember this part that tells you what is the spectrum of photons per dark matter annihilation. So there you have some uncertainty. But if you assume, say, BB bar, dark matter annihilating to BB bar, it's something like 50 GeV or so. And this point can move a little bit up and down, left and right, assuming we channel, but not horribly much. It's always this like 50 to 100 GeV, 30, say, to 100 GeV ballpark.
Okay.
And also sort of quite close to the thermal cross section. No, this is also the funny part, that it also seems, the properties seem quite on the money. All right, and so looking at gamma rays, it doesn't seem yet robustly excluded. Then if we look at multi-messenger, so let's see, as I showed you previously plot, antiprotons are another very good probe together with gamma rays, one of the most sensitive probes of dark matter, of WIMPs. And this is because we measure protons. So this is cosmic ray electron proton antiproton measurements that we have now thanks to AMSO2. It is quite precise. The error bars are tiny, up to TeV or so. And the proton, the blue spectrum, we know very, very, very well. And this proton spectrum is basically source. So antiprotons or secondaries are produced when protons in energy losses of protons. And so as we know proton spectra very well, we can predict antiproton spectra rather precisely, okay? And this is why, again, there are always uncertainties because we do not know so well the cross sections involved for this production and so on, but still that makes it one of the most sensitive probes. I will not, of course, go in detail here. You can ask me questions later, but for now, take it for granted. But also that, unfortunately, antiprotons seem to have excess also. Again, it's arguable, depends on the analysis, many analyses, some analysis you do not see it and so on. But it seems that also cosmic ray antiprotons at the moment cannot explain the galactic, cannot rule out the galactic center excess. So this is actually why I chose this as an example, because, so this is how you would do the search. If you have a signal, you would look multi-target, multi-messenger, but it also shows that it does not work always, quickly. So we have to wait more time, have better experiments and so on to know in the future which one is it. But this is in general how you approach the problem. And so in this case, what can we do? We can either take the Occam's razor perspective, which is what many people do, and in fact is very reasonable, saying, look, pulsars we know are in the galaxy, and they can also explain the galactic center excess, and because they're simpler solution, by Occam's razor, they should be the true one, which is really reasonable. And in fact, that's why many people believe. I mean, and pulsars can explain it really very, very, very well. And so, and also many analyses suggest that they are the more likely explanation. And also, I think Christoph also mentioned some novel analysis techniques that we can use in the future to actually be able to tell, really looking at the data, say it's this or that could be sensitive enough to really tell us just looking at the data. Okay, so I do not have any more time, unfortunately. I took it too easy. I will just skip this part because, so where is for me, what is the frontiers? So frontiers are, to increase sensitivity and to go to multi-TV ranges. And so for multi-TV, this is something, so multi-TV dark matter is also, it's the vanilla WIMP TV dark matter. And so here, as probably Laura told you, you have Sommerfeld effects, different particle physics effects that could boost your signal and so on. I will not, so the next generation array observatory CTA should be able to basically cross the thermal cross sections, also TV energies. So we should be in the next decade or so be able to probe the TV WIMPs as well. So this is a sensitivity projection. These are not actual limits yet, because this is what we believe CTA will be able to do. Okay. So for smoking guns, I will just do this very, very quickly in a minute. If I may, because again, I was mentioning often smoking guns, but never really got into that. I'm sure Francesca will do it tomorrow. So you can either look for spectral features. So because dark matter sometimes dark matter can produce also lines, sort of in cases where it sort of annihilates through box-like sort of diagrams to two photons. Okay, cannot annihilate directly to photons because it doesn't have charge, but box-like diagrams can produce two dark matter particles annihilating, say, to two photons, and then you would have really photons at dark, like with line, like really only photons of dark matter mass energy would be produced. So that would produce a very clear, line of gamma rays, and such lines are not expected from astrophysical objects. And therefore, you can just look for such line in dark matter spectra. And if you discover it, you can be quite certain, say that this is a dark matter signal. And people are looking for that. And it's a wonderful probe. And so by same logic in WIMPs, in ALPS, I wanted just to very briefly say, because again, Manuel will give you all wonderful lecture on ALPS. And indeed, these are already also even his slides. So I just want to just give you a little sneak peek in this context of general strategies, is that, for example, even in the context of axion-like particles, there is a wonderful smoking gun signature that one can look for, which is that, so let me just step back a second. So if you have axion-like particles can convert to photons in magnetic fields, okay? So And so what you look for, usually you look for gammas in the places, you look for photons in the places you have strong magnetic fields where you could expect that those axions can get converted in the signal that you can detect. And so, as we said before, like together with sort of dark matter density and so on, you also need regions with strong magnetic fields. But just to very briefly arrive to my point, we could, you know, so if there would be a supernova explosion in our galaxy, so, you know, if supernova explodes, neutrinos are the only particles that can escape supernova explosion right away. So usually if you have supernova, you discover, you observe huge neutrino signal initially that happened with supernova 1984 that happened in our galaxy. So you see surge of neutrinos, and they're precursors for photons that sort of get trapped in the supernova and come out somewhat later. Okay, and so usually when you have a supernova, you observe neutrino first, and then photons come with a delay. And what would be the smoking gun signature of axions is that if you would have a supernova and you would also have axions, say, present in nature, those would also be produced with this huge energy release in a supernova explosion, and together with neutrinos, those could escape a supernova. Okay, and so the point is that if there is no axions, you would expect neutrinos coming to Earth first and then photons, gamma rays later. If instead axions are present, then photons could come at the same time as neutrinos, as those photons would actually escape via the axion channel from a supernova. And so I do not want to say anything more there, but I just want to say these are the clever ways that people have taught about the smoking gun signatures, because there is no way in astrophysics that you could have neutrinos and photons and gamma rays come at the same time. Only if there is axion like. So detection of this coincidence would basically be a discovery of axions. So this is a wonderful example of how sort of thinking about what the smoking gun signature can be and the benefit it would bring. Because so this of course all relies on a supernova going off in our galaxy, which in principle should happen. We are due. One is due soon. Soon being tens of years. But if that would happen, such smoking gun signature could give you also probably of a large chunk of parameter space. Okay, so I will stop here. So just in summary, right, life is hard, but I hope I convinced you that this field of indirect searches is mature and growing, and that astrophysics is very exciting and we are learning a lot. And that we have a range of well-taught strategies sort of that we are ready and sort of getting there strategically in looking for dark matter signals. So in future, we should expect advances from astro theory. As I was telling you, there are these pulsar halos that have been discovered, galactic pevatrons, all this feeding in, the sophistication of our astrophysical modeling that then increases our sensitivity to dark matter searches. People are also working in analysis techniques, again from Christoph Stock, the ways how to sort of circumvent this sort of systematic uncertainty, all these uncertainties that plague your searches, how to deal with them in a smart way. And we will have a range of new experiments like the CTA, MEV gap will be closed at some point, when a Rubin observatory is saw. And then I wanted to leave you just with two motivational quotes, motivational, demotivational quotes, especially this, that it always seems impossible until it's done. So yeah, it's a hard search, but it's fun. And so, yeah. Okay, I stop here. I'm really apologizing for being over time.
Okay, thank you, Gabi, for a very interesting talk. And is there any more questions or comments? No? So if not, I will probably stop the live stream here.
I'm sorry. Yes,
okay.
I'm sorry. Pretty late. Could you explain a little bit more about this this excess in the central region of our galaxy?
I can, if you want, so because for the sake of time, if you want, because I'm sure that also Francesca will talk about, I cannot be sure.
Okay.
I would guess that she would also talk about this. And also I will be on, so let me just see the question. Right, so is there any, so just to answer first here, right, and so I will be on Gather Town as well, try to be on Gather Town as well, so then we could chat. Because it is a fascinating topic, I just sort of, I understand I went very quickly through it. But yeah, we could chat there if you want. Or if you have a very specific question that I can answer very quickly, I could also do that now. Bastian, what do you say? So something particular that bothers you about this, or
It's
more?
perfect. In the Gather Town, yeah, we can continue discussing.
Okay,
Thank
great. Thank you. Thank you. And then this question, is there any object made only of dark matter? Indeed, we do believe that very small halos. So I said that these dark matter, the dwarf galaxies, they're not only dark matter. They have also stars and so on. But these are like 10 to the 8, 10 to the 9 solar mass objects. Subhalos that are smaller than that, say 10 to 5, 6, or much smaller, are expected to be dark matter only objects because it would not be sort of trivial for such objects to contain a baryon component. So when one looks for sort of dark subhalos, one sort of has in mind objects like that. I don't know if only dark matter, but definitely, with negligible baryonic component. Okay, hope John, you, thanks. Good. Thank you for the question.
Okay, thank you. Any more question? Okay.